Bayesian probability is one interpretation of the concept of probability. In contrast to interpreting probability as frequency or propensity of some phenomenon, Bayesian probability is a quantity that we assign to represent a state of knowledge, or a state of belief. In the Bayesian view, a probability is assigned to a hypothesis, whereas under frequentist inference, a hypothesis is typically tested without being assigned a probability. The Bayesian interpretation of probability can be seen as an extension of propositional logic that enables reasoning with hypotheses, i.e., the propositions whose truth or falsity is uncertain. Bayesian probability belongs to the category of evidential probabilities. To evaluate the probability of a hypothesis, the Bayesian probabilist specifies some prior probability, which is then updated in the light of new, relevant data. The Bayesian interpretation provides a standard set of procedures and formulae to perform this calculation. The term Bayesian derives from the 18th-century mathematician and theologian Thomas Bayes, who provided the first mathematical treatment of a non-trivial problem of Bayesian inference. Mathematician Pierre-Simon Laplace pioneered and popularized what is now called Bayesian probability. Broadly speaking, there are two views on Bayesian probability that interpret the probability concept in different ways. According to the objectivist view, the rules of Bayesian statistics can be justified by requirements of rationality and consistency and interpreted as an extension of logic. According to the subjectivist view, probability quantifies a personal belief. Bayesian methodology. Bayesian methods are characterized by the following concepts and procedures: the use of random variables, or, more generally, unknown quantities, to model all sources of uncertainty in statistical models. This also includes uncertainty resulting from lack of information. The need to determine the prior probability distribution taking into account the available information. The sequential use of the Bayes formula. When more data becomes available, calculate the posterior distribution using the Bayes formula. Subsequently, the posterior distribution becomes the next prior. For the frequentist, a hypothesis is a proposition, so that the frequentist probability of a hypothesis is either 1 or 0. In Bayesian statistics, a probability can be assigned to a hypothesis that can differ from 0 or 1 if the truth value is uncertain. Objective and subjective Bayesian probabilities. Broadly speaking, there are two views on Bayesian probability that interpret the probability concept in different ways. For objectivists, probability objectively measures the plausibility of propositions, i.e., the probability of a proposition corresponds to a reasonable belief everyone sharing the same knowledge should share in accordance with the rules of Bayesian statistics, which can be justified by requirements of rationality and consistency. For subjectivists, probability corresponds to a personal belief. For subjectivists, rationality and coherence constrain the probabilities a subject may have, but allow for substantial variation within those constraints. The objective and subjective variants of Bayesian probability differ mainly in their interpretation and construction of the prior probability. History. The term Bayesian refers to Thomas Bayes, who proved a special case of what is now called Bayes' theorem in a paper titled An Essay Towards Solving a Problem in the Doctrine of Chances. In that special case, the prior and posterior distributions were beta distributions and the data came from Bernoulli trials. It was Pierre-Simon Laplace who introduced a general version of the theorem and used it to approach problems in celestial mechanics, medical statistics, reliability, and jurisprudence. Early Bayesian inference, which used uniform priors following Laplace's principle of insufficient reason, was called inverse probability. After the 1920s, inverse probability was largely supplanted by a collection of methods that came to be called frequentist statistics. In the 20th century, the ideas of Laplace were further developed in two different directions, giving rise to objective and subjective currents in Bayesian practice. Harold Jeffreys' theory of probability played an important role in the revival of the Bayesian view of probability, followed by works by Abraham Wald and Leonard J. Savage. The adjective Bayesian itself dates to the 1950s. The derived Bayesianism, Neo-Bayesianism, is of 1960s coinage. In the objectivist stream, the statistical analysis depends on only the model assumed and the data analyzed. No subjective decisions need to be involved. In contrast, subjectivist statisticians deny the possibility of fully objective analysis for the general case. In the 1980s, there was a dramatic growth in research and applications of Bayesian methods, mostly attributed to the discovery of Markov chain Monte Carlo methods, which removed many of the computational problems, and an increasing interest in non-standard, complex applications. Despite the growth of Bayesian research, most undergraduate teaching is still based on frequentist statistics. Nonetheless, Bayesian methods are widely accepted and used, such as in the field of machine learning. Justification of Bayesian probabilities. The use of Bayesian probabilities as the basis of Bayesian inference has been supported by several arguments, such as the Cox axioms, the Dutch book argument, arguments based on decision theory and de Finetti's theorem. Axiomatic approach. Richard T. Cox showed that Bayesian updating follows from several axioms, including two functional equations and a hypothesis of differentiability. The assumption of differentiability or even continuity is controversial. Halpern found a counterexample based on his observation that the Boolean algebra of statements may be finite. Other axiomatizations have been suggested by various authors to make the theory more rigorous. Dutch book approach. The Dutch book argument was proposed by de Finetti, and is based on betting. A Dutch book is made when a clever gambler places a set of bets that guarantee a profit, no matter what the outcome of the bets. If a bookmaker follows the rules of the Bayesian calculus in the construction of his odds, a Dutch book cannot be made. However, Ian Hacking noted that traditional Dutch book arguments did not specify Bayesian updating. They left open the possibility that non-Bayesian updating rules could avoid Dutch books. For example, Hacking writes, and neither the Dutch book argument, nor any other in the personalist arsenal of proofs of the probability axioms, entails the dynamic assumption. Not one entails Bayesianism. So the personalist requires the dynamic assumption to be Bayesian. It is true that in consistency a personalist could abandon the Bayesian model of learning from experience. Salt could lose its savor. In fact, there are non-Bayesian updating rules that also avoid Dutch books. The additional hypotheses sufficient to specify Bayesian updating are substantial, complicated, and unsatisfactory. Decision theory approach. A decision-theoretic justification of the use of Bayesian inference was given by Abraham Wald, who proved that every admissible statistical procedure is either a Bayesian procedure or a limit of Bayesian procedures. Conversely, every Bayesian procedure is admissible. Personal probabilities and objective methods for constructing priors. Following the work on expected utility theory of Ramsey and von Neumann, decision theorists have accounted for rational behavior using a probability distribution for the agent. Johann van Zyl completed the theory of games and economic behavior by providing an axiomatization of subjective probability and utility, a task left uncompleted by von Neumann and Oscar Morgenstern. Their original theory supposed that all the agents had the same probability distribution, as a convenience. Van Zyl's axiomatization was endorsed by Oscar Morgenstern. Von Neumann and I have anticipated the question whether probabilities might, perhaps more typically, be subjective, and have stated specifically that in the latter case axioms could be found from which could derive the desired numerical utility, together with a number for the probabilities. We did not carry this out. It was demonstrated by Van Zyl, with all the necessary rigor. Ramsey and Savage noted that the individual agent's probability distribution could be objectively studied in experiments. The role of judgment and disagreement in science has been recognized since Aristotle, and even more clearly with Francis Bacon. The objectivity of science lies not in the psychology of individual scientists, but in the process of science, and especially in statistical methods, as noted by C.S. Peirce. Recall that the objective methods for falsifying propositions about personal probabilities have been used for a half-century, as noted previously. Procedures for testing hypotheses about probabilities are due to Ramsey and de Finetti. Both Bruno de Finetti and Frank P. Ramsey acknowledged their debts to pragmatic philosophy, particularly to Charles S. Peirce. The Ramsey test for evaluating probability distributions is implementable in theory, and has kept experimental psychologists occupied for a half-century. This work demonstrates that Bayesian probability propositions can be falsified, and so meet an empirical criterion of Charles S. Peirce, whose work inspired Ramsey. Modern work on the experimental evaluation of personal probabilities uses the randomization, blinding, and Boolean decision procedures of the Peirce-Jastrow experiment. Since individuals act according to different probability judgments, these agents' probabilities are personal. Personal probabilities are problematic for science and for some applications where decision-makers lack the knowledge or time to specify an informed probability distribution. To meet the needs of science and of human limitations, Bayesian statisticians have developed objective methods for specifying prior probabilities. Indeed, some Bayesians have argued the prior state of knowledge defines the prior probability distribution for regular statistical problems, cf. well-posed problems. Finding the right method for constructing such objective priors has been the quest of statistical theorists from Laplace to John Maynard Keynes, Harold Jeffreys, and Edwin Thompson Jaynes. These theorists and their successors have suggested several methods for constructing objective priors: maximum entropy, transformation group analysis, reference analysis. Each of these methods has been useful in Bayesian practice. Indeed, methods for constructing objective priors have been developed by avowed subjective Bayesians like James Berger and José Miguel Bernardo, simply because such priors are needed for Bayesian practice, particularly in science. The quest for the universal method for constructing priors continues to attract statistical theorists. Thus, the Bayesian statistician needs either to use informed priors or to choose among the competing methods for constructing objective priors. Bibliography: Berger, James O. Statistical Decision Theory and Bayesian Analysis. Springer Series in Statistics. Springer Verlag. ISBN 0-387-96098-8. Bessier, Pierre, Mazer, E. Awakatzine, J. M. Metnachar. Bayesian Programming. CRC Press. ISBN 9781439,880,326. Bernardo, José M. Smith, Adrian F. M. Bayesian Theory. Wiley. ISBN 0-471-49464-X. Bickel, Peter J. Docsum, KJLA. Mathematical Statistics, Volume 1. Basic and Selected Topics of the Holden Day 1976 ed. Pearson Prentice Hall. ISBN 0-13850363-X. Mr. 443141. Davidson, Donald, Suppus, Patrick, Siegel, Sydney. Decision Making, An Experimental Approach. Stanford University Press. De Finetti, Bruno. Probabilism, A Critical Essay on the Theory of Probability and on the Value of Science, Inerkentnis, Volume 31, September 1989. De Finetti, Bruno, La Prévision, Ces lois logiques, Ces sources subjectives, Annales de l'Institut Henri Poincaré. De Finetti, Bruno. Foresight, its logical laws, its subjective sources. In H. E. Kaiberg and H. E. Smokeler, Studies in Subjective Probability, New York. Wiley, 1964. De Finetti, Bruno. Theory of Probability. A Critical Introductory Treatment. 2 volumes. Wiley, ISBN 0-471-20141-3, ISBN 0-471-20142-1. De Groot, Maurice. Optimal Statistical Decisions. Wiley Classics Library. ISBN 0-471-68029-X. Hacking, Ian. Slightly More Realistic Personal Probability. Philosophy of Science 34. 311-325. DOI 10.1086, 288169. JSTOR 186120. Partly reprinted in Garden Force, Peter and Salen, Nils Eric. Decision, Probability, and Utility. Selected Readings. 1988. Cambridge University Press. ISBN 0-521-33658-9. Hajek and Hartman. Bayesian Epistemology. In Dancy, J. Sosa, E. Stupp. A Companion to Epistemology. Wiley. ISBN 1-4051-3900-5. Preprint. Hald, Anders. A History of Mathematical Statistics from 1750 to 1930. New York. Wiley. ISBN 0-471-17912-4. Hartman and Sprenger. Bayesian Epistemology. In Bernecker and Pritchard. Rutledge Companion to Epistemology. Rutledge. ISBN 978-0-415-96219-3. Hazewinkel, Michiel, ed. Bayesian Approach to Statistical Problems. Encyclopedia of Mathematics. Springer. ISBN 978-1-55608-010-4. Howson, C. Urbich. Scientific Reasoning. The Bayesian Approach. Open Court Publishing Company. ISBN 978-0-8126-9578-6. Janes E. T. Probability Theory. The Logic of Science. Cup. ISBN 978-0-521-59271-0. McGrain, S.B. The Theory That Would Not Die. How Bayes' Rule Cracked the Enigma Code, Hunted Down Russian Submarines, and Emerged Triumphant from 2 Centuries of Controversy. New Haven. Yale University Press. ISBN 9780300169690, OCLC 670481486. Morgenstern, Oscar. Some Reflections on Utility. In Andrew Schotter. Selected Economic Writings of Oscar Morgenstern. New York University Press. pp. 65-70. ISBN 978-0-8147-7771-8. Pierce, C.S. and Jastrow J. On Small Differences in Sensation. Memoirs of the National Academy of Sciences 3. 73-83. Fanzel, J. Subjective Probability Derived from the Morgenstern von Neumann Utility Theory. In Martin Schubuck. Essays in Mathematical Economics in Honor of Oscar Morgenstern. Princeton University Press. pp. 237-251. Fanzel. In cooperation with V. Bauman and H. Huber. Events, Utility and Subjective Probability. Theory of Measurement. Wiley. pp. 195-220. Ramsey, Frank Plumpton, Truth and Probability, Chapter 7 in The Foundations of Mathematics and Other Logical Essays, reprinted 2001. Rutledge. ISBN 0-415-22546-9. Stigler, ed. M. The History of Statistics. The Measurement of Uncertainty Before 1900. Belknap Press, Harvard University Press. ISBN 0-674-40341-X. Stigler, ed. M. Statistics on the Table. The History of Statistical Concepts and Methods. Harvard University Press. ISBN 0-674-83601-4. Stone, J.V. Download Chapter 1 of book Bayes' Rule. A Tutorial Introduction to Bayesian Analysis. Sebtel Press, England. Winkler, R.L. Introduction to Bayesian Inference and Decision. Probabilistic. ISBN 0-9647938-4-9. Updated Classic Textbook. Bayesian Theory Clearly Presented.